Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we want to verify that the integral from negative infinity to infinity of e to the negative gamma x squared cosine 2 lambda ax equals root pi over lambda e to the minus lambda a squared. And to approach this problem, we're going to use contour integration. We're going to consider the integral of from minus infinity to infinity of e to the minus lambda z squared, e to the I 2 lambda az dz. Note that this equals note that the integral here on the left, when we expand out e to the I z 2 lambda az, we get cosine 2 lambda az plus I sine 2 lambda az, but sine is an odd function, and so integrating from minus x to x is going to give us 0, and so we're left with what we want, this integral that we started with. And now we're going to do some contour integration and integrate around a rectangle. So we're going to integrate from x comma 0, going counterclockwise, x comma 0, xa, and we're doing this in the complex plane, so it's x plus ia, minus x plus ia, back to minus x0, back to x0. And so now we want to first note our integral is really going to be the one on the bottom that we want. So now we're going to examine these two sides and the top line. So this side line, we have x constant. This is going from 0 to a. And also, we want to rewrite this in a slightly more manageable form quickly. So after rewriting this integral in factoring out e to the minus lambda a squared, we're left with e to the minus lambda z minus ia squared. This form looks a little bit nicer. Now we're going to examine our integral from x to x plus ia. Take the absolute value, note that it's less than the absolute value of this thing, which is just itself because it's a positive real number. It's less than the absolute value of the thing inside the integral, which gives us the real part of the thing that we're raising e to, and that's e to the minus lambda x squared minus y minus a squared, that whole thing times lambda. Now note as x goes to infinity, this thing on the right side goes to minus infinity, so e to the minus infinity, that goes to 0. This whole thing is approaching 0. So as we let x go to infinity, this line on the right is the same for this line on the left, because x squared minus x plus x doesn't matter. These integrals are both going to go 0. And so that simplifies our problem a good chunk. Now we're going to look at the integral along x plus ia to minus x plus ia. So now we're going to look at the line integral from x plus ia to minus x plus ia of e to the minus lambda z minus ia, z minus ia squared dz. And note that because all along this line our imaginary part is plus ia, we really just need to consider the z minus ia as our real part, which is just x. So this is really equivalent to integrating from x to minus x of minus lambda z squared dz, and using the well-known, this is the well-known integral, at least e to the minus x squared dx from 0 to infinity is root pi over 2. Substituting, z equals root z prime equals root z, we get this integral right here is really equal to minus root pi over lambda times e to the minus lambda a squared. So now we calculate our 3 line integrals that are not the ones we really want. But we also know from the fact that this is analytical in this whole region that the contour integral is always equal to 0. And so adding up all our integrals, we get so using the fact that we know this contour integral is equal to 0, we have all our line integrals. The bottom one is the one we want. Integral from minus infinity to infinity, e to the minus lambda x squared, cosine 2 lambda ax dx. Now we calculate the top one, which as we let x go into infinity, it's just minus root pi over lambda e to the minus lambda a squared. And the other two, as x goes to infinity, are just 0. And so we get our answer, that this integral is equal to root pi over lambda e to the minus lambda a squared. And that solves our problem. Thanks for watching. Please check out standardmath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.